Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 56, and this problem asks us to propose a structure consistent with each set of data. So compound A has this molecular formula, IR absorption, and this HNMR data. So let's determine first the degrees of unsaturation for molecular formula A. So we know that the degrees of unsaturation are the number of double bonds equals, equals the number of carbons, which is 8, minus the number of hydrogens plus halides over 2, so it's 10 over 2, which equals 5, minus the number of nitrogens over 2, so 0 over 2, plus 1. So we have 8 minus 5 is 3, plus 1 equals 4. So now we know here we have 4 double bonds or 4 degrees of unsaturation. Well, what does the IR data tell us? The IR data tells us that we have an sp2 and an sp3 hybridized carbon-hydrogen bond. And what does the HNMR data tells us? Well, we have a triplet which has 2 neighbors at 1.4, a quartet representing 3 hydrogens, that means 3 neighbors at 3.95, and we have a multiplet representing 5 hydrogens at 6.8 to 7.3. So we know that these 5 hydrogens right away are going to be aromatic. So right away, let's draw an aromatic benzene ring. And we know that these are aromatic because they fall in the range of 7 to 8 ppm. And not only that, we know that there's going to be 5 hydrogens on this aromatic ring. So now we know that one of these substituents is going to actually be the rest of our moiety to create this molecule. Not only that, I just satisfied my 4 degrees of unsaturation. 3 of them are from the double bond. The fourth one is from the cyclical structure. So we have 1, 2, 3, 4 for the cyclical structure. So now we know that we completed or we satisfied the degrees of unsaturation. So now let's look at this splitting pattern. Well, we have 5 more protons that we're interested in. We have a triplet that is neighbored to 2, and we have 2 hydrogens that neighbor to 3. So it's very obvious that if we have 3 hydrogens that are neighboring 2, then these 3 hydrogens will act as a triplet, just like this, and these 2 hydrogens are neighboring 3 hydrogens, so they would be a quartet. So we know that this would be our structure, but hold on, we just forgot this oxygen. So we actually need to add an oxygen in between the benzene ring and these groups to satisfy our molecular formula. Because we know that the benzene ring is not involved in any sort of splitting, so it's okay to add that oxygen here. So now I actually need to draw an oxygen, and then I can bond this. So now this becomes my overall structure. So we have oxygen, then an ethyl group on this benzene ring. Well, what about in B? So B, let's determine degrees of unsaturation again. So in number of double bonds, or the degree of unsaturation, equals the number of carbons, which is 9, minus number of hydrogens plus halides over 2. So we have 10 over 2, minus number of nitrogens over 2, 0 nitrogens over 2, plus 1. So we have 9 minus 5, 4, plus 1 equals 5 degrees of unsaturation. So what does the IR data tell us? Well, 1669 peaked. Well, we have a carbonyl group in this molecule. Now, the NMR data, we have a singlet with 3 hydrogens, singlet with 3 hydrogens, doublet 2 hydrogens, and doublet with 2 hydrogens. But these 2 doublets are in the range of aromatic compounds, 7 to 8 ppm. So we know that we're probably going to have an aromatic ring in this molecule. So let's draw this aromatic ring. And right before, we know that the cyclical structure is 1 degree of unsaturation. Then we get 2, 3, 4 degrees of unsaturation. So we know that the carbonyl group will be the 5th degree of unsaturation. So let's draw that carbonyl group right off the benzene ring. And I'm doing this, why? Well, because I know that I have 3 hydrogens that are singlets. So I know that by having a carbonyl group like this, these 3 hydrogens are going to be neighboring a carbon that has 0 hydrogens attached to it. So the neighboring will be 0. So 0 plus 1 equals that singlet that we see here. But now I still have an extra oxygen, and I need to add another CH3 to this molecule. So what I can do is I can just add another oxygen, another CH3, because I know that the CH3 is also a singlet, and we don't want any splitting to occur with the hydrogens on this benzene ring, like here or here. So we add the oxygen first and then the CH3, because oxygen and nitrogens cannot be involved in any splitting. So these three hydrogens will show up as a singlet. But another way I could draw this molecule could be this, but it could also be something like this. So we have that aromatic ring with our carbonyl group, but now we add the oxygen here, and then the triplet or the three hydrogens will be here, and this will still be a singlet. Then my methyl group will be here off of this carbon, because now its neighboring carbon, this one, does not have any hydrogens either, so this would still be a singlet. So given this data, it's actually hard to distinguish between these two, but it's going to be one out of these two forms. Either one is acceptable.